and dynamic load carrying capacity. Already we have started discussion on this topic. Learning objective of the today's session, they explain the static load capacity, dynamic load and load life, and derive or specify Stribeck equation. You know very well last time we have discussed what do you mean by static load. When shaft is stationary, load is acting on it. You can see it's the static one. And because of that, what is happening? It may produce a permanent deformation in rolling element in between ball and races. And how much this permanent deformation is permitted to define the static load capacity, its range is given, and in this deformation of point not one of the ball or roller diameter at the most heavily straight contact. We have already discussed these things. So therefore, we can define static load capacity of the bearing. It corresponds to a total permanent deformation of a ball or a races at the most heavily stressed point equal to this value, point not one of the ball diameter. But again here, in the manufacturer's catalog, already standard values of static load capacities for different bearings are given. But how to determine if someone is going to ask you? So that time you have to go for a Stribeck equation, and which is used to determine the static load capacity. Otherwise, the data of static load capacity, that is CO, which is available in manufacturer's catalog, you can refer that catalog. Now again, how to derive this expression or Stribeck equation? For that, you have to make some assumption, and the expression which is derived based on some assumption, that is races are rigid, balls are equally spaced, and balls in the lower half part only support the load. That means upper half part of the bearing or balls in the upper half part will not give support to the load. We have already discussed these things, and let us consider here CO is the static load. Here it is shown here. What is CO? And the balls in the lower half only support the load. All these are the balls here 1, 2, 3, and it gives support the load CO. That the P1 is the load which is acting on the ball. It gives the support to the load CO. Then similarly P2, P3. Likewise, you can add it P4. Depends on the number of balls used in bearing. Again here, as we have mentioned, races are rigid. That's why there is no possibility of deformation of the races. So what would happen when the static load which is acting on it, there may be possibility of shifting of the position of the races. Try to understand. And based on that here, when load is acting, the shift which is shown, and why it is going to shift? Because races are rigid. We have already discussed these things. From O initial position to O dash, and this shifting or this deflection of the race which is denoted by delta. For a ball 1, this deflection is delta 1. For ball 2, it's delta 2. If we are going to take this delta 2, and if we would like to find out here, suppose it's a vertical position or this axis, load which is acting here is the CO at ball 1, deflection is the delta 1, this one is the delta 1. For ball 2, this deflection of the race here is D2, and the vertical one is the delta 1, and angle made here is the beta. This is delta 2, this is delta 1, and angle made is beta. So how to find out delta 2? Delta 2 is equal to the delta 1 B or cos beta. You can use the relation or the geometry or trigonometry to find out it. Let us see how it is calculated. So first of all, we have to consider the equilibrium of the forces in vertical direction. And the load C0 which is acting on it, which is taken by all the balls. That's why the load taken by the ball 1, that is P1, ball 2, both the sides. That's why 2P1 cos beta and 2P3. Again, if you refer this diagram, you will find this ball 2, ball 2. That's why 2P2. Try to understand 2P3. In this way, you can make this equilibrium of the forces, and you will get this simple equation. CO is equal to P1 plus 2P2 cos beta plus 2P3 cos. And why cos here is taken? Because we are making it's the vertically equilibrium of the forces that we are doing here. Again, we have already discussed, as the races are rigid, the deformation delta 1 is at most heavily stressed portion that I have already told you, and how it is going to shifted through the delta 1. Okay, and inner rest shifts from position O1 to O dash without changing the shape as shown in our second figure. If delta 1 and delta 2 are the radial deflection at the respective balls, so you know very well delta 2 is equal to delta 1 cos beta. How? Once again I will elaborate. Look at this here. You will find delta 1 is the deflection for this. This is delta 1. And suppose this is ball 2, this deflection is the delta 2. This delta 2, this is delta 1, angle is beta. Then how you are going to find this deflection is delta 2, this deflection is delta 1. And for that purpose, what you have to do, you can easily find out delta 2 is equal to del 1 cos beta. Therefore, delta 2 by del 1 is equal to cos beta. Again here, according to Hertz equation, del this deflection is is directly proportional to p raised to 2 by 3. It's Hertz equation. Try to understand. We are using this Hertz equation here. In many books, it's available for the ball bearings. How much is the deformation is possible in terms of actual deformation? We are taking this is the delta 1. The delta is directly proportional to p raised to 2 by 3. If we are going to use this is for ball 1, the load is p1. Similarly, ball 2 delta 2 it becomes p2. So you can write del 1 is equal to c1 into p1 to raise to 3. Delta 2 is the deflection in ball 2, c1 into p2. c1 is the constant, try to understand. p2 raised to 2 by 3. And then you can take the ratio of delta 2 by delta 1. You will get this ratio p2 by p1 raised to 2 by 3. If you have a delta 2 by delta 1, why we are arranged in this way? Because we have a delta 2 by delta 1 is equal to cos beta. So you can substitute here this value cos beta is equal to this. So here it is written. Let us check in this way. The p2 by p1 raised to 2 by 3 is equal to delta 2 by delta 1. But delta 2 by delta 1 is equal to cos beta. So you can substitute here. You will get this equation. And similarly, you can find out here solid. You will get p2 is equal to p1 into cos beta raised to 3 by 2. Similarly, you can find out p3 is equal to p1 cos 2. Because here you will get here if you are going to see the bigger here for the p2 is the beta, here it becomes 2 beta. Try to understand. That's why here you will get, you can do it at home also. You will find this p3 is equal to p1 into cos 2 beta raised to 3 by 2. Now you have a p3, you have a p2. What you have to do, you have to substitute this p2 and p3 in this equation 1 or equation a. You can substitute p1 remains same, p2 means this value, p3 means this value. You can substitute here. After substituting, what you will get here, I am going to show you. Okay, 1 minute. Okay, after substituting this, you will get CO static load capacity is equal to P1 plus. I have substituted all these values here. You can again rearrange the term, solve this equation. Now here you have a P1 term. Now here you have a P1 term. You can take P1 common from this equation. This P1. So what is the remaining P1 in bracket 1 plus this for second term 2 cos of beta raised to pi by 2 plus 2 cos 2 beta raised to pi by 2. In this way you can arrange this equation. Okay, simple one. Many times in the same examination this derivation of this equation was asked. Okay, now again this is CO is equal to P1 plus this P1 into this bracket, but we are going to assume where this bracket is equal to M. Okay, you can assume this value 1 plus 2 cos beta raised to pi by 2 plus 2 cos 2 beta raised to pi by 2 plus dash dash is equal to M. M value, it's a M. That's why we can write CO is equal to P1 into M. And I have written this M is equal to this. Again, you know the bearing is circular one. That means total angle included 360. And what is the value of beta? It depends on Z. Z means number of balls used. When 12 balls, 15 balls, then you can find out the value of beta. You will get the beta from this. Again here, this Stribeck provided one equation based on these balls. When Z is equal to 8, Z is equal to 8, you will get beta. You can substitute beta here, you will get the M. That you can do this analysis. So you will get M is equal to, you have to use this equation, try to understand, and put beta based on this. If you are taking Z is equal to 8, you will get some beta, you can substitute here and here, you will get M, that is 1.84. If you are going to change Z, that is 10, you will get again M 2.28, 2.7. In this way you can do. Then Z by M, the ratio of this Z by M here you can calculate. If you will calculate, you will find, you will get, this is Z by M 4.35, Z by M 4.38, Z by M 4.36 and 4.37. That means here, if you are going to find out this ratio Z by M, practically you will find 4.35, 4.38, 4.37, 4.3. It means it's a constant. That's why Stribeck suggested we can assume Z by M is equal to 5 because it is in the range of 4.35 top to 4.37. It's a constant one. That's why here Stribeck suggested Z by M is equal to 5. And based on that, you can take M, Z by M is equal to 5. Therefore, M is equal to 1 pi by Z, this value. What you have to do, you can substitute this value here. So what you will get CO? The CO is equal to 1 by 5 into Z into P1. You will get this equation. But what is P1? P1 is the force required to produce a given permanent deformation. But this P1 is given by the equation K into D square. What is D? It's a ball diameter. What is K? K is a constant, depends on radius of curvature at the ball point and modulus of elasticity of the material used for the rolling element, that is ball. Based on that, you can easily find out the P1. You can substitute here, you will get the CO. So that's why replace P1 by KD square. Replacing the KD square, what you will get here? P1 is replaced by KD square. You will get CO is equal to KD square into Z by 5. And this equation is the Stribeck equation or Stribeck equation we can use to determine the static load of the bearing. This is about the Stribeck equation. It's okay. Then another important, some of the terms associated with rolling contact bearings are bearing life. How to find out the bearing life? That is very important because while selecting the bearing in your industrial gearbox design also, you have to assume how much time you are going to run this industrial gearbox, where 8 hours, 16 hours, 24 hours. And based on that, you have to assume the bearing life. And based on that, you are going to select the bearing for your particular application. But you know very well, bearing life is associated with the fatigue failure of the bearing elements, maybe in a race, outer race, cage, and the rolling element, that is balls or rollers. The fatigue plays important roles. That's why bearing life depends on, or it's limited by the fatigue failure. That's why while deciding the bearing life here, or while calculating or taking the value, how to decide the individual life of a bearing. So we can easily say that number of revolution which the bearing runs before the first evidence of fatigue crack in balls. That means number of revolution. If you have used a bearing, how many number of revolution that bearing can sustain before the first evidence of a fatigue crack. Fatigue crack means fatigue failure. You know very well. Already you studied it ME1, the design against fatigue failure. So that number of revolution is the bearing life. But it's very difficult to predict the bearing life of each or single bearing. It's very difficult. You have manufactured 1,000 bearing, and if you are going to find out the bearing life of each, the single bearing, it's very difficult task. It's very difficult to predict. That's why bearing life, it's okay. It's correct definition. Number of revolution that bearing can sustain before the first evidence, but it's very difficult to find out the life of a single bearing. Therefore, bearing life, which is taken into account, statical average performance of group of bearings are taken into account to decide the bearing life. Try to understand. That's why there are two criteria. One is average life of group of bearing, and second one is the rating life of group of identical bearing. Now first, let us discuss first one, the average life of group of bearing. That means the life of 90% of the bearing will reach out exit. Suppose average group, suppose there are 100 bearings. Out of this 100, 90% of the bearings which reach or exceed the life without fatigue failure. तो उसको बोलेंगे average life of the bearing. But we are not using this definition, or generally in the industrial practices we are not using the average life of the bearing. Try to understand. It's correct one, but we are not using. The rated life of the bearing is generally used, or rating life of the bearing. Rating life, which is measured by considering the identical group of bearing. Identical means the same group of bearings. Suppose 100 same group of bearings are manufactured, then you can check it how many number of bearings, that is out of this 100, 90% of bearing should complete or exceeds the number of revolution before the first evidence of the fatigue crack or its failure. Try to understand. So this is the correct rated life of the bearing generally used in industry. Try to understand. One is the average life, second one is the rating life, but rating life is used in industry. And what do you mean by it? Number of revolution that 90% of the bearing from the same identical group of the bearing will complete or exceeds before the first evidence of fatigue crack. Try to understand. The same definition, only out of that 100, 90% of the bearing should complete or exceeds before the first evidence. That is the rating life, and it comes under the statistical average. Okay, this rating life, the second one which is used in industry, this rating life is also known as minimum life, is also known as catalog life, is also known as L10 life, or is also known as B10 life. Try to understand. And this life is widely used in bearing. Try to understand. Okay. Then next important, this is about the bearing life. You know very well, sometimes if you are going to find out the median life of the bearing, so you know very well, sometimes the life which 50% group of bearing will complete. So out of 100, only 50% of the bearing complete. So you will get L50 life. The L50 is equal to, how to determine it? 5 times L10. L50 means 5 times L10. Try to understand this relation also. Sometimes in the examination, they may ask you to find out the L50. So what you have to do? You know the L10 life means 90% of the bearing can complete before the first particular or evidence of first. That is L10 multiplied by 5, you will get L50 life. It's okay. And you know the 90% of the bearing complete, that's why L10, that means 90% of the bearing complete. L50 means 50% of the bearing completes, that's why L50. Try to understand here. Then next one, dynamic load capacity. We have discussed static load capacity, then Stribeck equation, but what do you mean by dynamic load capacity? You know very well, there are two types of bearing, radial and axial. Some bearings may take a radial as well as the axial load. That's why while defining the load, we will say radial load in radial bearing or thrust load in thrust bearing that can be carried for a minimum life of 1 million revolution. Try to understand. Minimum life of 1 million revolution. The dynamic load capacity of bearing, how to define? The radial load in radial bearing, thrust load in thrust bearing can be carried by that bearing for a minimum life. And I have already told this rating life is known as minimum life, L10 life, B10 life. Okay, carried for a minimum life of 1 million revolution. You have to remember this thing. Minimum life of 1 million revolution. But what is minimum life? I have told. It's L10 life, or 90% of the bearing will reach or exceed before the fatigue failure. Don't make any confusion here. Minimum life means L10 life which 90% of the bearing will reach. Because on earlier side, I have shown what is minimum life here. Look at this. I have written here. This rating life is known as minimum life, catalog life, L10 life, B10 life. Try to understand. That's why here in dynamic load, radial load in radial bearing, thrust load in thrust bearing can be carried for a minimum life of 1 million revolution. This is the definition. But minimum life means L10 life, which 90% of the bearing. Already we have discussed this. There another term very important here, equivalent bearing load. In some of the bearings, you know very well, radial load is X, thrust load is X, and if this load acts on the bearing at a constant, this radial load or axial load, if it's applied on the bearing, it would give the same life as that bearing will attain in actual conditions. That's why the another term plays important role, that is equivalent bearing load. So what do you mean by equivalent bearing load? The constant load in radial load in radial bearing or thrust load in thrust bearing, if it applied to the bearing, it will give the same life as the bearing will attain under actual condition of the process in practical applications. That is equivalent bearing load. Try to understand. And that's why equivalent bearing load is a very important one. And by using equivalent bearing load, you can find out the relation between dynamic load, equivalent load, and bearing line to select the bearing. That's why while selecting the bearing, first you have to find out the dynamic load capacity, then you have to find out the equivalent bearing load. And how to find out this equivalent bearing load? It is given by P is equal to X into V into FR plus YFA. This equation you have to use to find out the equivalent dynamic, where P is the equivalent dynamic load, X and Y are the radial and thrust factors, V is the inner year return race rotation factor, and FR is the radial load and FA is the axial load. The X and Y, radial and thrust factor, V is the race rotation factor, FR, FY, radial and FA, axial load in bearing. Try to understand this equation is very important. And if look at this, I might have written here. This is the standard equation that you have to remember. But in many application or more than 90% application, you know very well, along with the shaft, which races is going to rotate? Inner race is going to rotate. And if inner race rotates, the value of V I have written for is equal to 1 for inner race. And that's why general equation, this equation in general, when inner race rotates, it x v is equal to 1, you can substitute. You will get x into fr plus yfa. That's why I have written this equation here. Okay. But when outer race rotates, you know, in some of the examples, outer race rotates and inner race is stationary. That time v is equal to 1.2 for outer race rotates. And in this case, when inner race rotates, v is equal to 1 and outer race stationary 1 in this case. Okay. Try to understand. The inner race rotation factor is equal to 1 when inner race rotates, and v is equal to 1.2 when outer race rotates. So you can substitute 1.2 for outer race and find out the P equivalent dynamic load. Now you have a dynamic load capacity in which dynamic load capacity is given by capital C. Static load capacity is given by CO. Okay. Then load life relationship. This is the very important term. What you have to do? The load life relationship. In load life relationship means L10 is the bearing life, but it's in million revolution. Try to understand. It's in million revolution. C is the dynamic load capacity. I have already told you dynamic load capacity. And P is the what? Already we have calculated now. P is the, what is this capital P? Equivalent dynamic load. Equivalent dynamic load. And equivalent dynamic load, how to calculate? XV FR plus Y FA. Already discussed on earlier slide. So you can find out. And what is this small p? The small p is the term which is having, which decides which type of bearing. Now let us see here. This small p is equal to this small p. I am highlighting this. Or you can arrange this term. C by p is equal to small t. You will C is equal to p in bracket L by 10 raised to 1 by p here. The value of p is equal to 3 for ball bearing. Try to understand. This P is equal to 3 for ball bearing, or this P is equal to 3 for ball bearing. And this small p is equal to 10 by 3 for roller bearing, or 10 by 3 for roller bearing. Try to understand. The value of this small p is equal to 3 for ball bearing is equal to 10 by 3 for roller bearing. So by using this equation, load life relationship, C is equal to, you can remember this, so you will get the dynamic load capacity. And this dynamic load capacity, once you have calculated the dynamic load capacity of the bearing, what you have to do? You have to check in catalog, manufacturer's catalog. If you are selecting one bearing, how much is the dynamic load? Try to understand. That's why you should know to calculate the dynamic load capacity. You have to calculate equivalent dynamic load. You have to calculate or decide L10. L10 means rated life of the bearing in mil revolution. If life of the bearing which is given in hours or working hours, so there is a relationship between life in million revolution and life in hours. That you can note down this. L10 is equal to 60 into N into L10H. L10H means life in hours upon 10 raised to 6. This equation you can use. So you suppose machine we are going to use for 8 hours. So you can use 8 hours here. L10 life means 8 hours. 60 into n into 8 upon 10 raised to 6. And what is n? N of rotation that bearing or shaft rotates at. So you can substitute that RPM here. You will get L10, L10 in million revolution, and after that you can substitute here. Then find out the equivalent dynamic load X V bar plus Y FA. So you will get the dynamic load capacity of the bearing, and this is required to select the bearing from manufacturer's catalog. In this way we can do the analysis. Thank you. This is about the what do you mean by static load capacity and what do you mean by the dynamic load capacity of the bearing. Okay, now